This is the third example of us using the second derivative sign diagram to determine where the graph is concave up and concave down and where the inflection points are. So the directions determine the x values of the points of inflection and the intervals where the graph of the function's concave up, concave down. Justify your answers. So we are fortunate enough that they already gave us the first derivative. So we got to find the second derivative. There's different ways we could do this. If we left it business as usual, we could use the quotient rule to find the derivative, and that would work out just fine. This particular problem, since the numerator is just a constant, I actually think it would be less work if I rewrote this as 3 times x squared minus 3 to the negative first. Now, if it's not something that you would have thought of or something you don't want to do, then don't do it that way. So if I find the second derivative, so let's head this. I'm trying to find critical values. If I want to take the second derivative, this is the chain rule. Put the negative 1 in front. It's going to be negative 3. Inside function stays the same. Subtract 1 from the exponent. Negative 1 minus 1 is negative 2. Then I multiply it by the derivative of the inside. The derivative of x squared minus 3, well, that's 2x. If I write this as a fraction, in the numerator, I got negative 3 times 2x is 6x. The denominator, since this is to the negative 2, is going to be this binomial squared. Then, once we found the second derivative, we need to know when is the second derivative equal to 0? When is the second derivative undefined? The first derivative, the second derivative is equal to 0 when the numerator is equal to 0. It's undefined when the denominator is equal to 0. So it's when 6x equal to 0, so we get x is 0. And it's when x squared minus 3 squared is equal to 0, which we're going to end up with plus or minus 3 square root style. So we got critical values for this of x equals negative square root of 3, 0, and positive square root of 3. If we then make a second derivative sign diagram, this is f double prime. We label the intervals. We got a negative square root of 3. We got a 0. We got positive square root of 3. So we need to figure out in each of these intervals, let's make sure this is legible, positive or negative in each of these intervals. So we pick a test point, which you don't have to disclose. I'm going to disclose what I'm going to use since you're taking notes on the AP test. You don't have to say what your test values are. So we are breaking these into these 4 different groups. And we are plugging this in to the second derivative. We want to know in each instance, is it positive or negative? Keep in mind, the bottom is positive every time. The number of positives that you're multiplying or dividing by has no effect if the answer is positive or negative. It's the number of things that you're multiplying by or dividing by that are negative. So if I put a negative 10 in this numerator, it's going to be negative. Negative divided by positive is negative. If I put a negative 1 into the numerator, it's going to be negative. Negative divided by positive is negative. If I put a 1 into the numerator, it's positive. Positive divided by positive is positive. If I put a 10 into the numerator is positive. Positive divided by positive is positive. Here's what this tells me. To the left of negative square root of 3, this graph is concave down, because it is negative. hold on a second. I got something. Oh, I made a mistake. Whoopsie, whoopsie, whoopsie. This is a negative 3 times a 2x, which is negative. That does not affect this work over here, but it certainly affects each of these. I apologize. Let's redo. Sorry, I did not catch that earlier. Phooey on mooey. If I put a negative 10 into this, negative 6 times negative 10, well, that's positive. Changes everything. Negative 1 times negative 6 is positive. Changes everything. Put a 1 into this, negative times a positive is a negative. Put a 10 into this, negative 6 times 10 is negative. Whew, good thing I caught that. Late, but not too late. If the second derivative is positive, then that means f is concave up. And that same thing can be applied here. If f double prime is negative, then f is concave down. And here, same thing is concave down. On the AP test, you would not have to write this stuff in blue. Just kind of making some notes here. Actually, it's completely redundant. I don't need to do that. So the original question was, determine the x values of the points of inflection. We did that. Well, actually, we haven't done that. And the intervals where the graph is concave up or concave down. So here's what we can say. We can say that f double prime is bigger than 0, positive, on the interval from negative infinity to negative square root of 3 in union with negative square root of 3 to 0. What conclusion can we draw from that? Conclusion that we can draw is that f, the original function, is concave up on these intervals. Yeah, I'm just going to erase this. It's just ugly. It just clouds up what we're doing. Just writing it down here. Similarly, we could say f double prime is less than 0 on this interval and this interval. So that's from 0 to the square root of 3 in union with square root of 3 to infinity. Therefore, the original function f is concave down on these intervals. Now we answered the second part of the question. Determine the intervals where it's concave up and concave down. We didn't answer where the points of inflection are. Point of inflection is where the concavity changes. This is the only place where there's going to be a point of inflection. So we would say f double prime changes sign at x equals 0. Therefore, f has a point of inflection at x equals 0. Done. We've answered the question. All right, hopefully that example made sense.